Hello friends, welcome to the course Essentials of Data Science with R Software 2, where we are trying to learn the topics of sampling theory and linear regression analysis. And in this module on linear regression analysis, we are going to talk about the concepts of simple linear regression analysis. So up to now what we have done, that we have considered a general form of the simple linear regression model, which has only one independent variable. We have estimated the regression parameters. Because the regression coefficients, which were beta 0 and beta 1, they have been estimated as b 0 and b 1. Now, one more question arises. You have estimated beta 0, beta 1 by b 0 and b 1 on the values of a sample of data. If the sample changes, then what will happen? Do you think that the same values of b 0 and b 1 will be obtained? Answer is no. These are sample dependent values. So, as the sample changes, these values will be changing. And why? Because they are the function of random variable. Y is my random variable in the simple linear regression model. So, your b 0 and b 1, which are the estimators of the regression coefficient, ordinary least square estimators of beta 0 and beta 1, they are the functions of y. Hence, they are the function of a random variable. So, obviously, as the values of the variable changes, these values will change. Once this b 0 and b 1 becomes a statistic, a random variable, then obviously the concept of variability comes into picture. The concept of coefficient, this confidence interval comes into picture. Just by estimating the values b 0 and b 1 will not help, but you also need to tell that how much is the variation involved in the values of b 0 and b 1. Second thing is this: you have assumed the random error to have a variance sigma square. But would you not like to find out what is the amount of random variation in my data? Yes, so that can be obtained by estimating the parameter sigma square. So, essentially we had three parameters in this case: beta 0, beta 1 and sigma square. So, we already have estimated beta 0 and beta 1. Now, we will try to estimate sigma square also. So, in this lecture I will try to do all the things, and also I will try to show you that how these things can be obtained in the R software. Well, when I try to show you the outcome in the R software, there will be many more things, but I will try to consider only some part of that outcome, and remaining part I will try to take up when we try to discuss the multiple linear regression model. Okay. So, now how to find out the variance of b 0 and b 1? Well, I do not know. Now, how to obtain it? So, obviously first we need to do some algebra, and we have to study the properties of this b 0 and b 1. I do not know whether these are good estimator or bad estimator, because we have just obtained the values. These values can be good, these values can be bad. So, how to assure that the values which you have obtained through b 0 and b 1, they are good values, and hence your model is good. So, for that we need to investigate the theoretical properties of b 0 and b 1. Okay, so, I will try to give you the details of the theoretical properties, and I will try to connect it with the data sciences. Okay, so, let us now begin with our lecture. First, I try to give you the outcome, and then I will try to show you the proof, right. So, you have considered the model y is equal to beta 0 plus beta 1 x plus epsilon, right, and we have obtained this beta 0 and beta 1. How? Beta 1 is obtained by b 1, which was sxy upon sxx, and beta 0 is obtained by B 0 y bar minus B 1 x bar. So, you can see here this depends on y, this also B 1 also depends on y. So, hence they are statistic, they are estimator, they are random variables, right. So, now once they are estimators, we would like to see whether they have nice properties or not. So, whenever we come to any statistical estimation procedure, there are several criteria, there are several properties through which we try to check whether the estimator is good or bad. First property is say unbiasedness, then we have another property variability, then we have consistency, then we have sufficiency, and we have completeness. I am not writing it in any order, right. They are these different properties are trying to give different type of information, but here I am going to consider this unbiasedness, variability and consistency, and sufficiency and completeness will automatically follow there. Okay. So, first let me give you the final outcome. Both B 1 and B 0, they are the unbiased estimator of their respective regression coefficient. Expected value of B 1 is equal to beta 1. So, B 1 is an unbiased estimator of beta 1, and similarly expected value of B 0 is equal to beta 0. That means, B 0 is an unbiased estimator of beta 0. Now, in case if you try to find out the variance of B 0 and B 1, then they are finally obtained as variance of B 1 is given by this expression sigma square upon S x x, variance of B 0, this is given by this expression which is sigma square times 1 upon n plus x bar square upon S x x. And if you try to find out the covariance between B 0 and B 1, this will come out to be, after doing some algebra, minus x bar upon S x x sigma square. So, now you can observe here one thing, that if you want to know the amount of variation or covariation of these estimators in your data set, you have to compute these three values, but they are dependent on sigma square, which is the population value, and you do not know. So, if you really want to know these values for a given sample, then you need to find the value of sigma square, which we can denote as a sigma square hat. Once you obtain the value of sigma square hat, then you can replace sigma squares in these three expressions by sigma square hat, and you can compute the sampling variability. Okay, so, that is what I am trying to show you here. So, that is the final result that we are going to obtain after doing some algebra. We will consider here a quantity which is called as sum of square due to residuals. So, you remember that on the last turn we had obtained the residuals E 1, E 2, E n. So, you simply try to find out their sum of squares, sum of E I squares, and this is called as sum of residuals, which is here like this. So, an unbiased estimator of sigma square is this quantity small s square, which is sum of square due to residual divided by n minus 2, right. So, how it is obtained, that I will try to show you in the further slides. So, now I try to do one thing, that in this expression what we have obtained here, this sigma square will be replaced by s square, this sigma square will be replaced by s square, and this sigma square will be replaced by s square. So, that is what I am doing here in this slide, and thus we can find out the unbiased estimator of variance of B 0 given by variance of B 0 hat and variance of B 1 hat, and the estimator of covariance between B 0 and B 1 as covariance between B 0 and B 1 hat. So, I simply have replaced this sigma square by here s square. So, based on this we can compute the standard errors of B 0 and B1. So, what we have to do? We simply have to take the positive square root of variance of B0, that will give us the standard error of B0, and then we try to take the positive square root of variance of B1 hat, and that will give us the standard error of B1. So, simply try to take the positive square roots of the estimators of variances of B0 and B1. So, that will give us the standard errors. Right. Okay. So, now the first question comes. First, I try to show you that how these things are obtained in R software. So, I will try to use the same data that I use in the earlier say lecture, where we had obtained the 20 observations on the students on their marks and that number of hours they study. So, but before that, in order to extract the information on the variances of B0, B1 means their estimate and the value of sigma square, we try to use the command here summary. So, summary of the lm y tilde x, and but this command will give you several outcomes, and you have to identify that which of the outcome is going to give you the standard error of B0, B1 as well as the value of sigma square. So, before I try to go to the R console, means I have taken here the screenshot to explain you in a better way, right, or if you wish I can show you first on the R console, so that you have a confidence on me that whatever I am doing here, this is correct. So, I try to take here the command here. And I already had entered this data. So, y is here like this, x is here like this, sorry, x is here like this, and now I try to find out the summary command. You can see here these are the values. So, I have just taken the screenshot of the same thing on this slide. So, now in this output you have to just look for a minute, so that you can see there is something like here this part. You can see here this is the intercept term and this is here x and this is here estimate. So, this part is known to us, this is the value of B0 75.79 and this is the value of B1, that is 3.4, right. Okay. After this there is a column standard error. So, this is actually trying to give you the value of standard error of intercept term B0, and this is the second value which is trying to give you the standard error of the regression coefficient associated with x. And here there is another thing which I have marked in red box. This is residual standard error. So, this is trying to give you the value of s. So, if you try to square. So, now in order to explain you these things more, I have taken the snapshots of this, and they are actually here. If you try to see, they are here. So, first I try to look at the snapshot number 1. It is trying to give you here residual standard error is equal to 18.65 on 18 degrees of freedom. So, what is this degrees of freedom? Because I will try to explain you later, but you can imagine that you are trying to estimate sigma square by sigma square hat is equal to s square, and this is here a random variable, and this random variable will have a sampling distribution, and this sampling distribution will actually turn out to be related to chi square, and the chi square will have certain degrees of freedom. So, these degrees of freedom are mentioned here, right. So, we had learnt that an unbiased estimator of sigma square was obtained here like this. So, this is trying to give you the residual standard error, means it is trying to take the positive square root of this quantity, and this quantity here is S, which is equal to 18.65. So, this will give you an idea about the variation in the degree in the data. So, now degrees of freedom are computed by n minus 2, which are 20 minus 2 is equal to 18 degrees of freedom, right. So, that is the interpretation of first part. Similarly, if you come to the second snapshot, say 2, which is, you can see here, this is here, right. So, I am just copying and pasting it here. So, these are the estimates. So, this is the value of B0, this is the value of B1, and these are the standard error of B0, and this is the standard error of B1. How they have been obtained? We had obtained that the estimate of variance of B0 is given by this factor, and if you want to find out the standard error, you have to take the square root of this estimated variance. So, it is trying to compute it on the basis of given set of data, because x and y are known to us. So, you can compute all these quantities S square, x bar square, Sx6, and this value turns out to be 12.78. And similarly, this quantity here 0.4379, this is the standard error of the regression coefficient, which is estimated by B1, and this is the standard error here like this. So, we had seen that the estimate of variance of B1 was obtained by the expression S square upon Sx6, and if you try to take the positive square root, this will give you the standard error of B1, which is here coming out to be 0.4379. So, this is how you are going to interpret these two outcomes from the software, right. Okay. So, now to convince you that whatever we have used, how they have been obtained, and how we can assure that the properties of unbiasedness, standard error, etc. are correct. So, now I am going to consider the proofs of these results. So, I will try to give you a brief description, but my request is that unless and until you do this proof yourself using your own pen, own book with your own hand, it is difficult for you to understand. So, I will try to give you the steps here, but you are requested to do the same thing yourself. So, we had obtained here B1 by Sxy upon Sx6, and B0 was y bar minus B1 x bar, right. And both, if you try to see, they are the linear combinations of yi's, they are the function of yi's. So, at least if I try to consider here B1, this I can write down as, say, B1 is equal to summation xi minus x bar yi minus y bar upon, say here, Sx6, right. So, in case if I try to write down this quantity here as, say, ki, so I can write down here this thing here as, say, k goes from 1 to say n ki yi minus the y bar, right. And if you try to make it more simpler, this will become I goes from 1 to n k I y I minus y bar summation I goes from 1 to n k I, right. And summation k I, if you try to see, this is summation x I minus x bar upon Sx6. So, this is n times okay, I can write down it, summation x I minus n times x bar upon Sx6, and summation x I is your n x bar minus n x bar upon Sx6. So, this becomes here 0. So, that is why I am trying to write down here B1 as summation k I y I, right. So, and you can verify there the summation k I is equal to 0 and summation k I x I is equal to 1. Okay. So, now if you try to take the expectation of B1, then I can write down I goes from 1 to n k I expected value of y I, and expected value of y I here is B0 plus B1 x I, because expected value of I is 0, right. So, hence I can write down this quantity here as a summation k I beta 0 plus summation beta 1 times k I x I, so, right. So, summation k I is 0. So, the first part becomes 0 and summation k I x I is equal to 1, that you can verify. So, I get here expected value of B 1 is equal to beta 1, that is, and that establishes that B 1 is an unbiased estimator of beta 1. Similarly, if you want to check the unbiasedness of B 0, then we try to consider here expected value of B 0 is expected value of y bar minus B 1 x bar. So, if you try to find out the value of y bar, this is your beta 0 plus beta 1 x bar. Yeah, do not write that that epsilon bar is equal to 0, because you have to remember one thing, we have made the assumption that expected value of epsilon is 0. That means this is over the whole population, 1 over population size I goes from 1 to the entire population, epsilon I is equal to 0. But when I am trying to write down here epsilon bar, this is 1 upon n, summation I goes from 1 to n, epsilon I, this will not be equal to 0, but when you try to take the expected value of epsilon bar, then this will become 1 upon n, I goes from 1 to n, expected value of epsilon I, which is equal to 0. So, this is what I have done here, and then minus here B 1 x bar. So, if you try to just take this quantity B 0 plus B 1 x bar, because x is stochastic, x is non-stochastic, x is fixed. So, I can take out this quantity outside the bracket, and expected value of B 1 x bar, this is that we already have proved that expected value of B 1 is beta 1. So, I can write down beta 1 x bar. So, these two terms get cancelled out and we get here beta 0. So, this B 0 is also an unbiased estimator of beta 0. Okay. So, after establishing the unbiasedness property of B 0 and B 1, let us try to find out the variances. So, we are assuming here that since epsilon i's are IID, they have got mean 0 and variance sigma square. So, this yi's are also independently distributed. They will not be identically distributed, remember, because expected value of yi is beta 0 plus beta 1 xi, and it depends on xi. So, if xi is changing, this mean will be changing. So, I can only assume here that yi's are independently distributed. So, since I already have expressed B 1 as say here summation k I yi, so I can write down the variance of B 1 as summation k I square variance of yi plus double summation k I k j and covariance between yi and yj. But since I am assuming that yi and yj are independent, so this covariance will become 0, and this part, the second part will become simply 0. So, the variance of B 1 comes out to be simply here k I as summation k I square, summation I goes from 1 to n k I square, and variance of yi is fixed sigma square. So, this variance comes out to be sigma square times summation k I square, and which is here like this. And if you try to simplify it here, this is sigma square sxx, this quantity is nothing but your sxx. So, 1 sxx gets cancelled out here, and you get here the variance of B 1 as sigma square upon sxx. So, you can see it is not difficult. And similarly, if you want to find out the variance of B 0, so variance of B 0 it can be written here like this, because B 0 was written as y bar minus B 1 x bar. So, this will be variance of y bar plus x bar square variance of B 1 minus twice of x bar covariance between y bar and B 1. So, we already have obtained the variance of B 1, but we have not obtained the covariance between y bar and B 1. So, we try to find out the covariance between y bar and B 1 using the basic definition can be written here like this, and if you try to substitute the value of y bar and expected value of y bar and B 1 minus expected value of B 1, you can simply just simplify this expression to this thing, and if you try to substitute here the value of here yi, well, you can obtain it directly also, but to make it more simple, I will ask you to just substitute here this value of yi as beta 0 plus beta 1 xi plus epsilon I, and try to simplify it here. I have given you here the complete expression, and you can see here once you take this expectation sign inside, means all the terms are becoming 0. the first term will become 0 because summation epsilon I is 0. This term also becomes 0 and this term also becomes here 0, and you already have proved that this is equal to 0, right. So, all these terms will become 0. So, covariance between y bar and B1 comes out to be 0, and hence variance of B0 comes out to be 1 upon n x bar square plus Sxx. So, hence I can write down now here variance of B0 here like this, variance of y bar that we know, that is sigma square by n. So, you substitute it and you will get here the same expression which we have written earlier. Okay. And one thing you have to notice here that this is here a bracket sign, right. So, this epsilon I will play an important role in making all these expectations to be 0. Similarly, if you try to find out the covariance between B0 and B1, so that will be simply covariance between y bar and B1 minus x bar covariance between B1 and B1, which is variance of B1. So, you already have proved that this quantity is 0. So, and variance of B1 you already have obtained, just substitute it here and you will get the covariance between B0 and B1. So, you can see that it is not difficult, and after this I am just going to give you one property, very important property. I am not going to do the proof here. This is called the BLUE property, BLUE, BLUE property, and this property is also mentioned as say Gauss-Markov theorem, which states that the ordinary least square estimator B0 and B1 possesses the minimum variance in the class of linear and unbiased estimator. What does this mean? If you try to take any parameter, say beta, beta can have different estimators, beta 1 hat, beta 2 hat, many things. First of all, you try to sort out all the estimators which are unbiased. So, some of them will be biased, some of them will be unbiased. So, you try to choose here all the estimators which are unbiased. Now, you try to find out the variance of each of the estimator which are unbiased. Then you will see out of these estimator, the estimator which is based on ordinary least square estimation, say B, that will have the smallest variance. So, this property assures that the way you have computed the value of beta 0 and beta 1 using the B0 and B1, that is giving you an value which is unbiased and which has got the minimum variance. So, you can believe on it that these are very good values, and we call it as if, and we call it as that they are the best linear unbiased estimator. So, this here B, L, U and here E, BLUE, right. So, this property helps us in assuring that the way you have obtained this numerical value, they are going to give you the good value, right. Now, I try to obtain the estimator of sigma square, but before that let me try to do some homework. We try to define here a quantity residual sum of squares. Residual sum of squares is denoted by SS res, SS added the subscript RES. This is defined as sum of squares of the residuals. So, this is sum of I goes from 1 to n EI square, which can be written as summation yi minus yi hat whole square. The values of yi hat can be written here as a B0 plus B1 xi, and if you try to write down here all these things over here, and then I can simplify this quantity as summation yi minus y bar minus B1 xi minus x bar whole square, and if you try to open it, this will come out to be the summation yi minus y bar whole square plus the square of second quantity and the cross product of first and second quantity, right. If you try to identify what are these things, the first term is your SYY, which is summation yi minus y bar whole square. The second term is B1 square, and this term here is Sxx. And what about the third term? Third term, if you remember, B1 was summation xi minus x bar yi minus y bar upon summation xi minus x bar whole square, which is sxx. So, this quantity summation xi minus x bar yi minus y bar can be written as b1 times sxx. So, this quantity here is written as say b1 sxx, and so this becomes here minus twice of b1 square sxx. So, if you try to simplify it, just try to substitute the values of b1 here, I can obtain this expression over here, and finally this will come out to be like this syy minus s square xy upon sxx. And if you try to write down this quantity as a sxy upon sxx into sxy, so this can be written as syy minus b1 sxy. Right. So, this is the form of SS res. Okay. Now, we can obtain the estimate of sigma square using this SS res. Right. Since and you can see here this SS res is a function of yi's, and now we assume here that yi's are say normally distributed. They have got a normal distribution with mean beta 0 plus beta 1 xi and variance sigma square. So, I am now trying to associate a distribution with yi, because if you want to use the property of chi-square, the random variable yi has to be normally distributed. So, assuming that yi is normally distributed, this SS res has a chi-square distribution with n minus 2 degrees of freedom. Well, I am not giving you here the proof, because that is a part of statistics and we use it, that is a standard result. So, I can write down here SS res upon sigma square will follow a chi-square with n minus 2 degrees of freedom, and in case if I try to find out the expectation of a chi-square random variable, then the expectation of a chi-square random variable is the same as the degrees of freedom. So, my random variable here is SS res divided by sigma square, and which is equal to here n minus 2. So, I can write down here expected value of SS res is equal to n minus 2 times sigma square, and from there I can write down here that sigma square hat is SS res divided by n minus 2, right, or even I can write down here it in a much simpler way, SS res upon n minus 2 is equal to sigma square, and from there I can obtain that sigma square hat, and sigma square hat has been indicated by S square. So, now S square becomes an unbiased estimator of the sigma square, right. So, now you can see these things are not very difficult, and once you have obtained the estimate of sigma square, now you try to consider the variance of B0 and B1 and try to replace sigma square by S square here. So, this will give you the estimators of the variance of B0 and variance of B1, and if you try to take the positive square root of this quantity, so this will give you the standard errors, right. So, it is not difficult at all, you can see a little bit knowledge of statistics and small algebra is only needed to obtain these things. Well, after that, just for your information, possibly these properties may be useful for you. I am just trying to state here simple properties of this estimator, that if you try to obtain summation xi ei, this will come out to be 0. If you try to obtain summation yi hat ei, this will come out to be 0, and summation of yi hat and summation of yi, they are the same. And the fitted line which you have obtained, this will always pass through the sample means x bar and y bar. Well, these properties are not actually difficult to prove. If you try to look into any of the book, it will just a matter of only couple of minutes. So, do not think that these are very difficult. So, that is why I am not giving you here, but my objective, as I said, it is essentially to motivate you to for decision sciences and for data sciences. So, that is the reason I am not giving you the proof of these properties. So, now we come to an end for this lecture. Now, this lecture was very important, at least in my opinion. Why? Because I established that whatever you are trying to compute those values have to be good values. So, you are trying to compute beta 0 and beta 1. So, you have to assure that you are computing a good value. So, for that I have given you Gauss-Markov theorem, and that will ensure that those numerical values are good. Good in the sense of having some nice statistical properties, right. And then I have shown you that different outcomes of our software, they are not coming from sky, they are simply computed. And one should know that how they are computed, because that will help at a later stage. How? When you are trying to work with a very huge data set, then you will not have an opportunity to look the data physically with your eyes, but you have to look into these values. For example, if you find that the value of sigma square hat or S square is coming out to be very huge, then possibly you can look into the data set, and possibly you can do something to control the variability first, because if the data has lots of variability, your model will not be good. That is the first principle. Sometimes whatever outcome you are getting here, they may not really match with what is happening in the real life. These types of observation will trigger inside your mind and would try to indicate that there is something wrong somewhere. Where wrong? That we do not know. We have to look into the data, we have to look into these values, and we have to find what wrong is happening at what point, because of this the outcome is not matching with the real values. For example, sometimes you see that the coefficient of the beta 1 is coming out to be negative, whereas you can see that when the values of independent variables are increasing, then the response is also increasing. So, why this is happening? There can be some reasons. For example, although I am not considering here, but if you try to see such an outcome, that will trigger in your mind that, well, there can be a problem of multicollinearity in the data, and then you try to look into those those tools and try to solve the problem. As I said, whenever the data comes, data will not follow your rule, data will have its own rules, that will have its own conditions, and you are the one who should know how to control those conditions and get the good outcome. So, that is why it is very important for you that just by looking at the outcome of the software will not be helpful, but you must know that what are the values which are being computed, so that if the software outcome is not matching, you can look back into your analysis and try to use better tools, maybe some other type of analysis. Right. So, okay. So, now you practice, you think about it, and I will see you in the next lecture. Till then, goodbye.